So for quiz 3, we have experiments 6, 7, and 8 content that is going to be tested. In experiment 6, we have all these topics, experiment 7 and experiment 8. And let me just walk you through these topics. The goal over here is just to kind of um, remind you that this is the kind of thing that we have been talking about since we have gone to this the remote learning. So experiment 6 started with talking about transistors. We looked at bipolar junction transistors, the NPN type, and we looked at how we can take that transistor. We essentially tried to connect a few topics together. The concept of switches and how we can use a transistor in those two extreme cases of cutoff region and saturation region to do the switching. We we looked at the circuit models for all the logic gates. We did that in the context of where the switches are located, and where they are located in terms of series and parallel, that dictates essentially what kind of logic gate that you implement. Then we moved on to two components that are based off of op amps that allow us to convert an analog signal into a binary signal. One was the comparator, which has a problem of noise. It doesn't tolerate noise. And then we looked at the Schmidt trigger, which has two different thresholds. So it needs a lot bigger voltage to transition from one state to the other. And by doing that, it removes or it tolerates noise much better. So comparators and Schmidt triggers are definitely going to be there on the exam. Please review that. If it's your strength, really good, you can move on. But if you want to review some topics, comparators and Schmidt triggers, you should expect it on the exam for sure. Then in experiment 6, we also talked about digital switching. So how can we use those 7400 ICs? Specifically, we looked at the 7404 and 7414. These are both NOT gates. One of them does not have Schmidt trigger response, but 7414 has a Schmidt trigger inverter operation. So those are the major topics in experiment 6. I also want to point out that all this information is in a very detailed manner listed on the class website. So if I go into EI webpage, let's see right here, and go into information about quizzes and click on quiz 3. If I scroll down, you can first of all, you can take a look at all the back exams. Actually, I want to point out one problem in the most recent back exam, so I'll open that up. But there are lots of back exams over here starting from fall 2007, so a lot of material that you can use as practice. However, if you do 3 or 4 exams, that is a good amount of practice as far as looking at back exam is concerned. But if you go further down, you will take a look at several topics. So inside each topic, there are specific skills that we try to test. And please take a look at that. These are all essentially the same things that we are talking about in experiments 6, 7, and 8. But they are more detailed, and they are, providing you specific details about what to learn. So a lot of topics there. So please feel free to do that after the lecture. Um, let's come to experiment 7. In experiment 7, we started talking about logic gates. We looked at AND, OR, NOT, NAND, NOR, XOR, XNOR. So a lot of 8 different types of logic gates. We talked about De Morgan's law and how we can use that to simplify gates and combinational logic. We studied the combinational versus sequential logic, so things that have memory and things that don't have memory, and how do we implement memory in circuits using the cross-coupled feedback configuration. Then we focused on the JK flip-flop, jump kill flip-flop. We used the 74107 IC to look at the hands-on experience on JK flip-flop. We also looked at the 4-bit counter in 74393. We also learned how to convert binary to decimal values in case we wanted to look at a certain counter state like 0010. What does that correspond to in decimal? by using positional significance, or simply multiplying that with increasing powers of 2 and adding the result up. You can convert that binary to decimal number. And then the 555 timer, the astable mode, that was essentially the big one. So this particular topic, you can expect a design problem on the 555 timer. We studied this in a lot of detail. We spent a lot of time taking a look at the internal configuration of the 555 timer. So how can we use the characteristics? So for example, how can we use R1, R2, and C1, change those parameters to generate a square wave of a desired frequency and duty cycle? So we looked at that in the 555 timer. As I said, I want to show you guys one pretty good resource, especially for the 555 timer. So if you look at the most recent back exam for quiz 3, this is from fall 2019. The first problem itself is based on the astable multivibrator, which is our 555 timer. And some of these questions are pretty straightforward, where you just apply the equations that we actually derived in class, and to get the result. So for example, question A is asking you to find the on time and the off time and duty cycle. So given the values of the resistors and capacitors in the circuit, essentially we are going to be concerned with RA, RB, and C1 here. And because we are given those values, we can apply the formulas, find the results over here. So that's straightforward. Then we are asked to sketch the output waveform on a time axis. So if you know the numbers that you calculated in part A, you can apply that to part B and sketch that out. Again, pretty straightforward. But when you come down to part C and part D, that's when it gets a little bit more complex and interesting. So in part C, you're asked to find the maximum and minimum voltages of pins 6 and 7. And as you know, pin 7 is the discharge pin. So that's when, if the capacitor discharges to ground, it is going to discharge through R2 or RB in this case, but that happens through pin 7. So what are the minimum and maximum voltages on that? Take a look at the solution here. You have to apply voltage divider rule a couple of times to get that, and I have provided all the details here. Make sure that you understand the details of how to calculate this. Pin 6 and pin 2, that is pretty straightforward, because it goes from 1/3 VCC to 2/3 VCC and back and forth. So that's pretty straightforward. And then we sketch it at the end. So if you know the numbers over here, you can sketch it over here. That's fine. But part C, I feel that it is a little bit interesting and not so straightforward. Um, is there a question that you guys wanted to ask? I could hear someone in the background. Okay, if you do, feel free to type it up in the chat box. I will continue talking about the quiz 3 review. Let's see. We are done with this particular problem. Let's go back to this. Next, we have experiment 8. So it's the most recent experiment. We talked about diodes, different types of them, and we particularly focused on the applications of diodes. How can we use a diode to do a half wave rectifier, a full wave rectifier, a voltage limiter, and a voltage regulator using the Zener diode, LEDs, phototransistors. So all these topics, either the components or their applications, all of those things are the key to all those is the current voltage characteristic of the diode. So whenever you're trying to answer all of these questions, try to see if you can look at the IV characteristic and be in a better position to answer those questions, because it should be the case. If you understand the IV characteristic of diodes very well, then you should be able to answer questions related to that pretty comfortably. Okay, so I encourage you guys to take a look at the resources that are available on the EI web page for quiz 3. in terms of back exams or the specific skills that you should focus on, that should help with the preparation. Now, when I say logistics are going to be the same when compared to quiz 2, what I mean is there are going to be some problems that are going to be relatively simple, and I expect most of you to do really well on those things. But there will be things like we had one problem that was design based, on which the average was around 75%, and there is going to be a problem like that where there is going to be some design involved, which means that you will need to do some hand calculations. You need to also do some capture piece by simulations, and try to make sense of whether all of the things that you do, like for example the paper calculate the analytical calculations and the simulations, do they match, and how closely they match, so you can do all of that analysis in the design problem that will be given. But the point that I'm trying to make is there will be some capture piece spice, and I assume that for EI, since you guys have been doing a majority of your simulations on PSpice, you guys have become experts at capture PSpice by now. Okay, let's take a moment here. There have been some questions. All right, so there's a question about one of the problems. Let's see. Oh, absolutely. So the question is 2B. So how do you answer this question? So this is essentially saying that right now I have a JK flip flop. It's negative edge triggered JK flip flop, and I know that from the symbol itself. I have a bubble there. The desired output of the negative edge triggered flip flop after the pulse is Q0 Q bar 1. So I want to essentially reset or kill the output to 0. How can this be achieved? Well, there are several possibilities. But before you do that, you have to also pay attention to what is the current output. The current output given to us before the pulse is Q is 1 and Q bar is 0. So you have a 1 there and you have a 0 there. I want to make this 0. That means I want to toggle it. And I can do that by using the toggle state. In toggle state, I have J as 1, K as 1. I'm going to make sure that my clear signal is 1, which means that I don't clear my flip-flop. And then the moment I have the negative edge on the clock, I will have achieved my desired output. So using the toggle state is one option. The second option is to kill or reset. This is independent of the previous state. So I can make J0, K1, K is 1, kill is 1, reset it. Clear is still inactive, so it is 1. And the moment I have the negative edge on the clock, I would have obtained the desired output. The third option is to simply clear the flip-flop. And actually, this is independent of the clock. So the 7-4, well, I didn't say it was a synchronous or asynchronous JK flip-flop. So if this is a 74107 flip-flop that we studied, it is actually independent of the clock. It gets reset. So Q becomes 0, Q bar becomes 1 the moment you make clear 0. So it doesn't matter what J is, it doesn't matter what K is. If you make clear 0, meaning connected to ground, the output will become 0 and Q bar will become 1. So those are your three options that you can use to get the desired output. So I hope that answers the question regarding 2B. I noticed that project 3 wasn't mentioned. So the quizzes mainly focus on experiments. So project 3, project 4, these are not going to be some things that we test you on. So materials that we have been learning on during the experiments, that is going to be tested on. So the essentially the difference is in project 3 we have the monostable mode of the 555 timer, which is not going to be a part of the exam. Okay. No problem. Can you go over how to get the formula for V7 max? Okay. So um, uh, let's see. Right. So it's coming back to the same question about problem 1, and I feel like this is not a very trivial problem to solve. So let me take a moment or two to answer. How do you find the minimum and maximum voltages on pin 7, for example? Pin 6 is fine, 2/3 and 1/3 of VCC. We know VCC to be 9 volts in this example. So 1/3 of 3, 1/3 of 9, and 2/3 of 9 will give us our V6 min and max. That's fine. And then when we discharge, V7 minimum should be 0, because when we discharge the capacitor, we are essentially connecting pin 7 to directly to ground. So that's 0, which is indicated by that red flat 0 there. But V7 max is needs some thought. So let's try to look at this. I want to look at this pin, discharge pin, that's the bottommost line here, which is essentially voltage across RB plus voltage across C1. So V7, voltage at point 7, is the sum of voltage across RB and voltage across C1. So by summing up those two voltages, I can get voltage at pin 7. However, I'm interested in the maximum voltage at pin 7. So what can I do? I can take whatever the maximum voltage is going to be across capacitor and add whatever voltage is going to be across the resistor at that time. So what is the maximum voltage across the capacitor? Well, that is going to be the maximum voltage at pin 6. So that's 2/3 of VCC. So that way we get the first number. What is that? V6 min, max, sorry, 6 volts. We get the first number right away. And then we have to sum up voltage across RB. Now, voltage across RB can be obtained by using voltage division. So I know voltage at point C is 6. Voltage at point A is 9. So voltage across both RA and RB should be 9 minus 6. So 3 volts. 3 volts is divided between RA and RB. And voltage across RB should be 3 times RB divided by RA plus RB. So you'll be using voltage division. So if I do all of that, as is done over here, VRB is VCC minus V6 max. So all of that calculation is showed in gray here. You find out the voltage across RB, you plug that number back in here to get that value. So I hope that brought some clarification. And if it didn't, then this video is obviously getting recorded and it will be posted on YouTube. I suspect that a lot of students will have a question about this. So I will refer to them. I will refer them to the video with the specific time mark. Okay. Let's see. All right. So I think we are doing well with the questions so far. We talked about quiz 3 topics. Let me see. What should I do next? Let's do project 4. Get excited, people. So in project 4, in my opinion, in a lot of students' opinion, project 4 is the most interesting project for the entire EI class, because here we build an optical communication link. So we will have a optical transmitter, and we'll build an optical receiver. Over here we will have an LED that transmits light, And on the other side, we'll have a phototransistor which will detect light. And we are going to transmit an audio file, a song, through light between the optical transmitter and receiver, and perhaps we can try to play it on a speaker. Let's see how this goes. So, this design involves a lot of steps, a lot of components, and we do not have the those at hand. So I have already built the transmitter and the receiver. My goal is going to be to talk about some key concepts about this project, which shouldn't take more than 15-20 minutes. And then I will do the demo. All right, so what are we doing in the transmitter? The goal is we are going to take light pulses, and we are going to encode an audio signal. So I have, say, a song, an audio signal. I'm going to encode that using light pulses. So how do I encode? Well, let's take a look at this. This guy is showing you the audio signal, and this guy is showing you the encoded signal. And as you can see over here, if you have a bigger amplitude on the audio signal, then you have a bigger width of the light pulse. And if you have a smaller amplitude on the signal, the audio signal, then you have a narrower width on the pulse, light pulse. And then of course at the end you are increasing again, so increase again. This technique is called pulse width modulation. We are modulating or changing the width of the light pulse depending on the amplitude of the signal. So a stronger voice, or a loud voice, is going to be indicated by the light as pulses that are on for a longer amount of time. And a very quiet sound amplitude or signal amplitude is going to be indicated by the light going very small, and very narrow in terms of its on time. So it changes on off relatively quickly. So that's pulse width modulation. That's what we are doing with project 4. So we are going to use the 555 timer to get the pulse width modulation exercise going on. And we know that we have three parameters of the 555 timer, two resistors and one capacitor that you can tweak to change how that pulse width modulation is going to happen. So how big are we going in terms of the width, and how small are we going in terms of the width? So all those limits will be set by the parameters that you connect around the 555 timer. So that's about the transmitter. The total design is, as I said, two boards. The first board is going to be the transmitter, which is indicated over here. And the second board, well, let's do this. That's the first board, and the second board is right here. And it is going to be truly optical if we don't share anything at all, right? So we don't share power supplies, we don't share any wire. They are supposed to be separate entities. The only thing that is going between them is the light sent from the LED detected by the phototransistor, and that's it. So you could have several blocks. So for example, block A could be take the input signal, a wave file, and sample it so that it becomes a pulse width modulated signal, and then perhaps send it to a LED. So those are going to be blocks A and B. And then in the receiver, after the photo detection, you might be interested in amplifying doing an audio amplifier, going through a low pass filter so as to smooth out the audio wave and eventually play it on a speaker. So those are certain blocks that go in, uh, and we'll take a look at what goes inside each of these blocks in just a bit. So the goal over here is to just understand how things are being done, not as much as actually doing anything here. So let's see. First, we'll take a look at the transmitter. So the transmitter, our light pulse width modulated light transmitter, is based off of the 555 timer. So over here, we are using the function generator or wavegen from the analog discovery to send out a audio file. So what we are going to do is we are going to import a song as a file that you can play using the analog discovery on the yellow wire. The first thing that we'll do is we'll do a DC block. That means that we'll remove the average of the signal. We'll block DC using capacitor. Then we'll feed it to the control input of the 555 timer. And control input is actually an input that goes into the threshold comparator. So we are actually changing the control voltage here. In the previous exercises, we didn't. On pin 6, we expect two resistors. There is one resistor R2 which is fixed. However, there is another resistor which is a combination of two resistors, as you can see. One is a potentiometer, a 100K potentiometer. So by using a knob or a screw, you can turn this wiper one way or the other so as to increase or decrease the resistance between 2 points, point A, point B. And the other resistor is fixed, 1K resistor. And what it does is essentially, as you are changing this knob, it is going to change the sampling rate for the function generator signal. So it's essentially going to sample the sound file at a faster rate or a slower rate depending on where you are in terms of the wiper. V1 is our power supply, and we are using the analog discovery to give the 5-volt power supply. We talked about the 555 timer, and the output of the 555 timer is going to be our pulse width modulated signal, which is going to be transmitted using the LED. There is also a 100 ohm current sensing resistor over there that is effectively protecting the LED. Capacitor C2 is actually the one that is getting charged and discharged, depending on the comparison that is happening inside the 555 timer. And we are comparing those voltages to what you see on pin 6 and pin 2, the threshold and the trigger pins. So this generates my pulse width modulated signal. What am I using for power over here? I'm using the analog discovery to provide for the 5-volt power supply. Next, in my receiver, this is by far the most complex circuit that we have looked at during the semester. There are lots of things happening over here. The first off, we have a 330 microfarad capacitor, which is essentially going to function as an element that will ground any high frequency signal that is present between those 2 points. We have a photo transistor. This is going to be our light sensor. We go from the light sensor to a DC block, remove DC, go into a, let's see, what is this? This is a non-inverting amplifier with a gain of 22. And this guy, the next chip, is an audio amplifier with a gain of 200. And in the middle, there is a 10K potentiometer. So a variable resistor where again there is a screw or a knob that you can turn that will take portion of the amplified op amp signal and let it go through to the audio amplifier. So essentially this is our volume control. And after the op amp, we have after the audio amp, we have RC connection, which is going to allow uh, uh, the amplified signal to get a little bit more smoother, and then eventually play on a speaker. We are using a 100 ohm resistor to protect our speaker, so that there is not too much voltage. There's not overloaded. It's the speaker is not overloaded. Let's see. One key thing that a lot of students have difficulty with when they are building this is the power supplies. So let me talk about the power supplies. You see two of them, 9 volt plus 9 volt and minus 9 volt. So how do you make those connections? So let me erase this out. Let me erase this so that we have some space to work. Let's talk about this 9 volt battery here first. We have two of them. So for that particular 9 volt battery, let me highlight that in red here. I'm going to use the power rail at the top, and I'm going to connect the red wire that is coming out of this guy to that. And the black wire from the 9 volt battery, I'm going to connect to that rail over there, where that's going to be my ground rail. So for the first power supply, you have the power rail and the ground rail that are in reference to this power supply, the plus 9. So you take the two leads of this battery, connected to that, red and black. Most people get here, but the next step is a little bit difficult. So let me erase this guy, let me erase this guy, and take a look at this negative 9 volt power supply. So this negative 9 volt power supply also has two wires that are coming out of it. There is a red one, there is a black one. But I need negative 9 to go into pin number 4, which means I have to connect the black wire from that supply to pin number 4 and connect the red wire to the ground rail. So it's flipped that way, but you still need two power supplies to go there. So that's how that is done. We are using two 9 volt power supplies to do the receiver. We are using an independent analog discovery power supply of 5 volts to do our transmitter. So I hope the some of the things about how to build the optical communication link are clear. The next step is to actually show you guys how it works. So to actually go ahead and demo it. So I will stop the recording here. In the meanwhile, you guys can take a break